size in the grounding electrode conductor, or GEC, for a separately derived system, you correctly size it according to the primary conductors that feed the transformer. This is in accordance with the National Electrical Code, specifically Table 250.66. Let's delve deeper into this process. Now, let's address the overcurrent protection, or OC, for the primary conductors of a transformer, for example a 30 kV ampere transformer with a 480 volt primary. The overcurrent protection, or OC, is indeed calculated at 125% of the full load current, or FLC. Let's illustrate this with an example. Imagine you have a 30 kV ampere transformer operating at 480 volts on the primary side. To determine the appropriate size for the primary conductors and their overcurrent protection, you would perform these calculations. Firstly, calculate the full load current, or FLC. The formula is FLC equals the transformer's kilovolt ampere rating divided by the primary voltage. In this case, it's 30 kilovolt amperes divided by 480 volts. This results in a full load current, or FLC, of 62.5 amps. Secondly, determine the overcurrent protection, or OC, required. According to electrical codes, you typically size the overcurrent protection at 125% of the full load current, or FLC, for transformer primary conductors. Therefore, multiply the full load current, or FLC, which is 62.5 amps, by 1.25, which represents 125%. This calculation yields an overcurrent protection, or OC, value of 78.13 amps. Thirdly, size the primary conductors. The primary conductor should be sized to handle at least the amount of the overcurrent protection, or OC, calculated. In the previous step, we determined the overcurrent protection, or OC, to be 78.13 amps. This means the primary conductors must be rated to carry at least 78.13 amps continuously. You would consult the appropriate ampacity tables in the National Electrical Code, specifically Table 310.16, to select a conductor size that meets or exceeds this ampacity requirement, considering the conductor's insulation type and installation conditions. In summary, firstly, calculate the full load current, or FLC, by dividing the transformer's kilovolt ampere rating by the primary voltage. Secondly, determine the overcurrent protection, or OC, by multiplying the full load current, or FLC, by 125%, or 1.25. Thirdly, select primary conductors with an ampacity equal to or greater than the calculated overcurrent protection, or OC, value, referring to the appropriate ampacity tables in the National Electrical Code, specifically Table 310.16. To reiterate, you size the primary conductors in accordance with the overcurrent protection, or OC, calculation. In the example given, the primary conductor should be sized to handle a minimum of 78.13 amps, based on the 125% calculation of the transformer's full load current, or FLC. Now, let's clarify some key points to solidify understanding. The grounding electrode conductor, or GEC, connects the separately derived system's grounding electrode to the system's grounded conductor, typically at the source, such as the transformer. Its primary purpose is to provide a low-impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. The size of the grounding electrode conductor, or GEC, is determined by the size of the primary conductors feeding the transformer, as indicated in National Electrical Code Table 250.66. This table provides guidelines for selecting the appropriate grounding electrode conductor, or GEC, size based on the size of the ungrounded conductors. The overcurrent protection, or OC, is essential for protecting the transformer and the primary conductors from overloads and short circuits. Sizing the overcurrent protection, or OC, at 125% of the full load current, or FLC, as permitted by the National Electrical Code, allows for the transformer's inrush current during energization without causing nuisance tripping of the overcurrent protection, or OC, device. However, it's crucial to select an overcurrent protection, or OC device that is appropriately sized to protect the conductors from overcurrent conditions. The primary conductors must be sized to carry the calculated overcurrent protection, or OC, value continuously without exceeding their ampacity rating. This ensures that the conductors can safely handle the expected load current and fault currents without overheating or causing insulation damage. The National Electrical Code, specifically Table 310.16, provides ampacity ratings for various conductor sizes and insulation types, taking into account factors such as ambient temperature and installation conditions. It's essential to consult this table to select conductors with an ampacity rating that meets or exceeds the calculated overcurrent protection, or OC, value. Ignoring the NEC requirements and best practices when sizing the Grounding Electrode Conductor, or GEC, overcurrent protection, or OC, and primary conductors can lead to various hazards and code violations. Firstly, undersized Grounding Electrode Conductor, or GEC, may not be able to effectively carry fault currents, increasing the risk of electrical shock and equipment damage. Secondly, improperly sized overcurrent protection, or OC, can result in inadequate protection against overloads and short circuits, potentially leading to conductor overheating, insulation damage, and even fire. Thirdly, undersized primary conductors may overheat and fail under normal load conditions, posing a fire hazard and disrupting power supply. The National Electrical Code, or NEC, provides specific guidelines and requirements for electrical installations to ensure safety and compliance. Ignoring these regulations can result in code violations, fines, and potential legal liabilities. It's crucial for electrical professionals and installers to adhere to the NEC guidelines and best practices when designing and installing electrical systems. When working with electrical systems, it's essential to prioritize safety to prevent accidents and injuries. To energize circuits before working on them whenever possible, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not qualified or experienced in electrical work, seek assistance from a licensed electrician to ensure the work is performed safely and correctly. Let's look at another example. Suppose we have a 75 kV ampere transformer with a 208 volt primary. Firstly, the full load current, or FLC, is calculated as 75,000 volt amperes divided by 208 volts, which equals approximately 360.58 amps. Secondly, the overcurrent protection, or OC, at 125% of the full load current, or FLC, is 360.58 amps times 1.25, which equals approximately 450.73 amps. Thirdly, the primary conductors must be sized to handle at least 450.73 amps, and you would select a conductor size from NEC Table 310.16 that meets or exceeds this ampacity. Fourthly, the Grounding Electrode Conductor, or GEC, size is determined based on the size of the primary conductors, as per NEC Table 250.66. Now let's discuss some additional considerations. When selecting the overcurrent protection, or OC, device, you need to consider the interrupting rating. The interrupting rating of the overcurrent protection, or OC, device must be sufficient to handle the available fault current at the transformer's primary terminals. This is crucial to ensure that the overcurrent protection, or OC, device can safely interrupt fault currents without failing. You'll need to perform a fault current calculation to determine the available fault current at the transformer's primary terminals. This calculation takes into account factors such as the utility source impedance, transformer impedance, and conductor impedance. Based on the fault current calculation results, select an overcurrent protection, or OC, device with an interrupting rating equal to or greater than the available fault current. Also, consider the type of overcurrent protection, or OC, device. Common types of overcurrent protection, or OC, devices include circuit breakers and fuses. Circuit breakers are resettable devices that trip open when an overcurrent condition occurs, while fuses are one-time devices that melt and interrupt the circuit. The choice between circuit breakers and fuses depends on factors such as application requirements, coordination studies, and personal preferences. Circuit breakers offer the advantage of being resettable, while fuses provide fast and reliable overcurrent protection. The National Electrical Code, or NEC, provides specific requirements for the installation and protection of transformers. These requirements cover aspects such as grounding, overcurrent protection, ventilation, and clearances. It's essential to comply with these requirements to ensure the safe and reliable operation of transformers. For example, transformers must be properly grounded to provide a low impedance path for fault current and to minimize the risk of electrical shock. The grounding system must comply with NEC Article 250, which specifies the requirements for grounding electrode systems, grounding conductors, and bonding. Also, transformers must be protected against overcurrent conditions using overcurrent protection, or OC, devices that are properly sized and installed. The overcurrent protection, or OC, devices must be coordinated with the transformer's thermal characteristics to prevent nuisance tripping and to ensure that the transformer is adequately protected against overloads and short circuits. Transformers generate heat during operation, so it's essential to provide adequate ventilation to prevent overheating. The ventilation system must be designed to dissipate the heat generated by the transformer and to maintain the transformer's operating temperature within acceptable limits. The National Electrical Code, or NEC, specifies minimum clearance requirements for transformers to ensure adequate ventilation and to prevent the accumulation of combustible materials near the transformer.